Now is time for lesson 2.3, logarithmic functions. And I am sure, or at least I suspect, some of you are like this when you hear logarithmic functions. So logarithms are very important throughout the calculus courses, and it's also where I see many, many mistakes in students' work. So this lesson is quite important for us. We begin with a definition of base A logarithm. Just like with the exponential functions, which we discussed last time, we need base A to be positive and not equal to 1. And then we can define the base A logarithm as follows. Well, it's really equivalent to an exponential equation that y is the log base A of x, if and only if x is a to the y. And the way that I usually remember this, I will write it like this, say log base A of x equals y, means a raised to the y is equal to x. I will put these little circular arrows to remember the correspondence. So let's look at these exponential equations just as an example. And what we're looking at here is this part. And let's write down the corresponding statement about a logarithm. This is our first exercise. Well, here we see log base 5 of 125 equals 3. And you can put the arrows to make sure this makes sense, right? This says 5 raised to the power of 3 equals 125. Now the next one, you see it says the log base 49 of 7 equals 1/2. Because, well, once again, 49 raised to the 1/2 equals 7. It's exactly what that, they are saying the exact same thing. One is phrased in terms of logarithms and one is phrased in terms of exponents. Well, some important notation here, ln x. This is the log base e. Log base e. And I would say that ln x comes up the most in the calculus courses for the same reason as I mentioned at the end of the last lesson, that the exponential function with base e comes up the most in calculus courses. But another one that you sometimes see is where you just see log and you don't see the base written explicitly. This is understood to be the log base 10. So this is base e. And this one was base 10. Let's talk about some properties of logarithms. And these properties are so important. Definitely, not only are important, they're also easy to mistake and confuse with other things. So I'll start with these three, and then we will say a few others. When you have a product on the inside of a log, this turns into a sum. So this will be log base A of x plus the log base A of y. When you have a quotient on the inside, this turns into a difference. So this is log base A of x minus the log base A of y. And then when you have a power, the power comes out in front. So this is r log base A of x. Let me put a box around these. One of them is if you take the log base A of 1. This says A to what power gives you 1? Well, this would be 0. Now, what does this mean in terms of the graph? Because over here, I will just say this one is the graph of a logarithm. I think it's the graph of ln x. But what this says, you see, if you think about the graph of the log, this would be the x value, and this would be the y value. And so this says that 1, 0 is on the graph of every logarithm. And you can see it here. Oh, it's right here. You see 1, 0 is on the graph. But then there's two more that I'll mention, and they have to do with the relationship between the logarithm and the corresponding exponential function. So if you take log base A of a to the x, we just get x. And if you take a raised to the log base A of x, we also get x. These last two are really statements about inverse functions, but I will leave them just written like this. Well, let's look at the graph now. And as I mentioned, I've just graphed the natural log, which is the most important one. And in purple here is the graph of e to the x. Now, what do you see? Well, maybe I should label one more thing before I ask that question. This dotted line is the line y equals x. So now you can ask yourself, what do you see? Well, what happens is you can just take the graph of e to the x, which we talked about the graphs of exponential functions last time, right? E was about 2.718. Certainly that base is bigger than 1. And so the general shape is something like this for y equals e to the x. But we take this and just flip it along the line y equals x. And we have the graph of the log base e logarithm, which is natural log. And I think this is very beautiful. It's really what happens with inverse functions. In any case, this is the graph of y equals ln x. From this, you see immediately we can write down the domain. Let's see, let's specify. This would be 4 f of x is log base a. It's much more general than just natural log, which we have graphed. But the domain, you see, it is not all real numbers. Here, this is a vertical asymptote. The domain is just positive numbers. In fact, this is the range of the exponential function. And similarly, the range of the logarithm, well, this is minus infinity to infinity. This goes down. And then this one, even though it grows slower than the graph of, say, f of x equals x, this will grow without bound. And so if you think about squashing the graph of y is ln x or y is log base a of x to the y-axis, you will fill out all of minus infinity infinity for the range. Wonderful. Well, let's move on. Let's do some examples. We want to solve some logarithmic equations. We're going to have to use properties here and the relationship between a logarithmic equation and an exponential equation. And so in this first one, that's really what I'm just going to be using. You see, this says 2 raised to the 2 will be x plus 3. Let's write that down. 2 to the 2 is x plus 3. And then this says 4 is x plus 3. We can just subtract 3 from both sides. We get x equals 4 minus 3, which is 1. This was our first example. Now let's move down. Here we have a sum of 2 logs. And so I want to use my property, first of all, that this is the log of, this would be 4x times x, or 4x squared, and this equals 2. Now you have to remember, looking at this notation, really, and I'll move this to add it, there is a 10 down here because log is log base 10. Well, here we go. This is 10 raised to this power of 2 is what's on the inside. So let's write it. We get 10 squared is 4x squared. Now this is 100. So we have 100 equals 4x squared. The next step would be divide both by 4. Maybe I will put an arrow here. And we get x squared equals 100 over 4, which is 25. Well, if all I'm solving is x squared equals 25, I would have 2 possible answers. I would have x equals 5 and minus 5. However, we have to go back to the original equation, which is here. And you notice that minus 5 is not in the domain of the logarithm. And so we will rule out this possibility. This cannot be it. So the only solution here is x equals 5. This is what I will underline. We had to think about domain to rule out one of the possibilities in that example. Now we have the log base x of 8 is 3 over 4. This one we can just convert. We would know x raised to the 3/4 power equals 8. Let's write that. X raised to the 3/4 power equals 8. Well, how would I go from here? Let's see. If I raise both sides to the 4/3, we have x to the 3/4 raised to the 4/3 equals 8 raised to the 4/3. This is going to be fantastic because left-hand side, power to a power, we multiply, we get x. And over here, we just have to evaluate 8 raised to the 4/3 power. So what I'll do first, we can take the cube root of 8. This would be 8 to the 1/3 and then to the 4th. And the cube root of 8 is 2. So I have 2 to the 4th. And 2 to the 4th is 4 times 4, which is 16. So here is my answer. X equals 16. We have one more logarithmic equation on this page. Here I have a difference. And so I'm going to, very much similar to this example, my first step is to use a property to write a quotient on the inside. I have the log base 5 of x divided by x minus 8 equals 1. Now, what does this say? It says 5 raised to the 1 is what's on the inside. So we have x divided by x minus 8 equals 5. How am I going to solve this? Well, I think here's what I will do. If I can just multiply through both sides by the denominator, I get x equals 5 times x minus 8. At this point, let's distribute the 5 across the parentheses. We will have x equals 5x minus 5 times 8, which is 40. Now we're in really great shape. In fact, we're almost done with this problem. I can just subtract 5x from both sides. X minus 5x is negative 4x. This will equal negative 40. And the only thing left to do is divide by negative 4. And I have my final answer. X equals positive 10. And this is wonderful. If you want to think about domain, which is not a bad idea, here that would be evaluating log base 5 of 10. This is fine. Here we'd be evaluating the log base 5 of 2. And this is fine also. So unlike here where we had to rule out one of the answers for a domain issue, we don't have that in this problem. So let's move on and let's use some logarithms to solve exponential equations. Most of the time, at least me personally, but most of the time I want to use the natural log. It just makes my life easier. Well, in particular here, 1, 2, 3 of the 4, they all have e in them. So I would choose natural log. But even in this one, I'm going to choose a natural log. The thing you'll notice in all 4 of these examples is I cannot just get the same base and equate exponents. That's what we did in the last lesson. But you see here, we're not going to be able to do that. And that's when we bring in the power of logarithms. So what I'm going to do on the left-hand side is I want to get an e to a power by itself. And how to start is I can just divide both sides by 2. So you see I have e to the negative 6x. This is going to be 10 over 2, which is 5. Now I'm ready to bring in a logarithm. I can take the natural log of both sides. This one is ln e to the minus 6x, and this one is natural log of 5. But you see what happens. Let me back up for 2 seconds. Here, we have ln of e to something. Okay, that's this line with base e. And what we get is just the exponent, you see? So we're going to get back here. It's going to be what is up inside the exponent of e. So here we have ln e to the minus 6x. The left-hand side is minus 6x. Minus 6x. and this equals ln 5. And my last step is just divide by -6. This is going to be an exact answer. I'm going to leave my answer exact rather than typing into a calculator and rounding. So here I get x is negative ln 5 over 6. This is my answer to this exponential equation. So now maybe I will do this one, which is similar. We'll move over. I want to try to get the left-hand side as a single power of e and then a number on the right-hand side. But initially I have to do a little bit of work. So what do I have here? I have e. Okay, we have e to the x, quantity squared. Power to a power, we multiply. So this is 2x. And then I have e to the 2 minus 3x. And this will be 4. One more step on the left. Now I have a product. I can add the corresponding exponents. So this is e. Well, when I add here, this and this, add them, we get just 2 minus x, because I have 2x minus 3x. So this is 2 minus x, and this is 4. Now I can come in with my logarithm. This is a natural log. Just as I did in the last example, we take the natural log of both sides of the equation, and the left-hand side becomes 2 minus x, and the right-hand side is ln 4. Let us subtract 2 from both sides. We get minus x is ln 4 minus 2, and then the last step is divide by -1, and so x will equal, well, this is going to be -4 ln 4 plus 2. This will be my answer here. This one is a little different. We'll do this one first. You see, once again, I have problems trying to get the same base on both sides of the equation. And I don't see e in it, but I'm going to start off by taking a natural log of both sides, and then we will use properties. But this is a fun one. So we have ln of 3 to the x equals ln of 4 raised to the x plus 1. I'm trying to solve for x. The thing is, you see inside the log, really on either side, I have a power. And one of our properties, in fact, is here. When you have a power on the inside, we may bring the power out in front of the logarithm. And so let's do that right here to both the left and the right-hand side. The left-hand side is x ln 3. And then the right-hand side is x plus 1 ln 4. Well, let's keep going. I'm going to distribute. Here I have a sum, and I will distribute. For the moment, I'm going to leave the left-hand side alone. So here I have x ln 4 plus ln 4. Let's subtract x ln 4 from both sides of the equation. We have x ln 3 minus x ln 4. And this equals ln 4. We're really almost there. Let's factor out an x. And now I'm ready to divide. You see, ln 3 minus ln 4 is not 0, so I can divide by it. And this will allow me to write my final answer. Let me do it right here. And then I will resize some things. So x will be ln 4 divided by this, which is ln 3 minus ln 4. This is my final answer. Last one on this page, we have e to the 2x plus 3 minus 6 e to the x equals 0. So we have some choices here. I think the way that I'm going to approach this is just try to have exponential on one side, and then I will have the other term on the other side. Kind of, and very much like in the spirit of these two, that's how I'm going to start off. So this would say e to the 2x plus 3 equals 6 e to the x. I just added that to both sides. Now let's take the natural log. We have ln e to the 2x plus 3 equals ln of 6 e to the x. Well, really on the left-hand side, I can go ahead and simplify this. We have 2x plus 3, but the right-hand side, I think I'm going to use a property that says I can write this as a sum. So this would be ln 6 plus ln of e to the x. Now, you see how fantastic this is. Ln e to the x is just x. Okay, let's write that. We have 2x plus 3. This is ln 6 plus x. And now you see, I'm almost there, in fact. I'll do it in 2 steps. First, subtract x from both sides. We have 2x minus x, which is x, and then plus 3 is ln 6. And now my final step, just subtract 3 from both sides. We get x is ln 6 minus 3. And this is my final answer here. Our very last page, well, take a deep breath, everyone. We have done so much with logarithms in a very short amount of time, but we have one more type of example, and we will do 2 functions. So we are given 2 different functions. Y is f of x. We want to expand the natural log of y using properties of logarithms. At this point, you might wonder, why in the world am I doing this? But let me say in Calculus 1, there's a beautiful technique for differentiation called logarithmic differentiation. And the very first step is to do exactly what we're doing here. In fact, both of these, this and this, I've had on tests before in Calc 1, where I asked to find the derivative using logarithmic differentiation. So we aren't differentiating today, but we will expand ln y using properties of logarithms. Let's get started. In this first one, we have ln y, okay, which would be ln of this cube root, and then we have a product of 3 things. So I am going to write, in my very first step, I'm going to write the cube root as a 1/3 power. This is 1/3, and then ln of, well, I can copy and paste. It's all of this. The question is, what do I do next? Well, I see a product. I have 3 things, in fact, multiplied. So I stated the property in terms of, if you have 2 things multiplied, you can break it into a sum. If you have 3 things multiplied inside of a log, you can break it into a sum of the 3 terms. And this would be our final step, or our next step. We have a third. Now, don't forget the parentheses, because we need to distribute them later, but this will be ln x minus 1 plus ln x minus 2 plus ln x minus 3. When we distribute, we just get 1/3 ln x minus 1, and then plus 1/3 ln x minus 2, and plus 1/3 ln x minus 3. This would be my final answer. But understand, this was not y. This is ln y. So this is ln y. Now we have one more where we will do the exact same thing. We are expanding as much as possible using properties of logarithms. And we have ln y equals ln of this whole thing, which is x squared plus 1 raised to the 3x divided by 5 to the x. Now, we're going to have to proceed in steps here. The first step, fundamentally inside of the log, I see a quotient. And so this will be, well, let's write it as a difference. We will have ln of x squared plus 1 to the 3x minus ln of 5 to the x, okay? Quotient on the inside becomes the difference of logarithms. Well, I need to keep going here. So In this first term, you see I have a power. So I can bring the power outside of the logarithm. This will be 3x times ln of x squared plus 1. And then I also here, I have a power on the inside. So I can bring this outside. This was similar to an example we did earlier. But this will be minus x ln 5. Minus x ln 5. Now here you note that I cannot do anything else to simplify. So I will just put equals ln y and draw my box. At this point, this is the end of lesson 2.3. You can get started on the exercises. Thank you so much.